So in chapter 7, we're going to discuss light, which is going to be in some ways very similar to our discussion about waves and sound. So in this chapter, we're going to talk about light sources, electromagnetic spectrum, the light interaction, diffuse reflection, law of reflection, image formation, refraction, dispersion and color, optics, light ray model, wave-like model, and then our current understanding about light. So sources of light. We have what we call luminous objects, which produce light. An example of something that's luminous would be the sun. On the other side of that spectrum, we have our non-luminous objects, which would be something like the moon. Now, another term that we use is called incandescent, and these are things that glow with visible light, meaning we can see them, from very high temperatures. So the image here is an incandescent light bulb, but really any fire, flame, is going to be an incandescent light source, as well as the sun. So the sun is both luminous and incandescent because the sun burns at a very high temperature along with wood and things like that. And so we have two different terms to describe sources of light. So the electromagnetic spectrum may not be new to you. The spectrum ranges from radio waves all the way up to gamma rays. But the only part that we really normally concern ourselves with at this level is what's called visible light. And it only makes up a really small portion of the entire spectrum. Within that visible light band, this is where all of our colors show up. The red, orange, yellow, green, blue, violet. And so visible light is given off from incandescent sources at high temperatures. So those sources we just talked about on the previous slide give off visible light. Now, the electromagnetic spectrum is important because it's going to combine electricity and magnetism, which we talked about in the same chapter, because they're also very closely related. So the electromagnetic spectrum is made up of waves. They're co-oscillating waves. So co-oscillating refers to that back and forth motion we talked about with vibrations, but they happen at the same time, which is what makes them co. So you'll have the electric field that we see here in blue. This is going back and forth, repeating in the plane of the paper. But then perpendicular to that, remember perpendicular is like this, making a T. So this would be coming out of the paper, back away from the paper, out towards you, and then back away from you. So if we were to look at it from right here, where we looked down the black arrow, it would look like this, where these are the the electric waves, and these are the magnetic waves. Okay, so they're regenerating because they repeat over and over and over again, and then they're perpendicular to each other, so the arrows are pointing at a 90-degree angle all the way through. So when we're talking about light, we're really focused on only this band in specific. Now, we see luminous objects because of the light they emit, but non-luminous objects are going to be seen by the light they reflect. So it's important to know that there's a difference between those two. Luminous objects are visible because they emit light. Non-luminous objects are going to be visible because they reflect light. Now, what happens at the surface between the light and the object is going to depend on the nature, or about three factors. One is the smoothness, the second is the nature, and the third is the angle. So, for example, if we have a very flat surface here, all of the sources of light are going to come in and they're going to bounce off this surface at regular, repeatable, identical type ways. But if the surface is not smooth, so it's jagged like this, we get what's called diffuse reflection, where it's not going to bounce off in nice, even ways. They're all going to kind of just bounce off in every which way and scatter. And we're going to call that diffuse reflection, we'll see in a few chapters, which is our main visibility method of how we see the world around us, because very few things in our world are 100% completely smooth. Now, the nature of the material is going to be whether it's translucent, like a window, or whether it's solid, like a wall. And then the angle of incidence, we're going to talk about that when we get to law of reflection in just a few slides. But the angle of incidence is basically looking at what angle the light comes in at. So when light interacts with matter, there's four possible interactions. We can have reflection, refraction, absorption, or transmission. And absorption and transmission are kind of opposite. So if we have this box here, it kind of shows you what's happening with each of them. So the incident light, meaning the source, so the incident light is always the source, like the sun. It's going to come in, and if it hits the surface that reflects it, it's going to beam it back out. So that's this right here. The moon is up here in the sky, but it's being reflected by the water. Okay, so that's reflection. That's why we see a reflection of the moon on the water. The other option would be whether light is absorbed. So we can see here that the light is absorbed by the object, and if the light comes out the other side, we're going to call that transmitted light. So transmitted light would be like the light coming through a stained glass window. It's going to pass through the window, the pane of glass, and then as you can imagine down here on the floor, there's going to be a replica of the stained glass. Another thing that could happen is how we detect colors. So white light coming in, this is the sun, or any really luminescent object. When we have white light coming into an object and all of the colors, orange, yellow, green, blue, purple, violet, are absorbed, the color we see is red. So look down at what you're wearing, your shirt, what color it is, and you may see red or orange or blue, yellow, purple. And the reason why you see that color is all the other colors of the rainbow are being absorbed except for the one that you see. And that light is reflected back at you, whereas all of the other colors are absorbed. We're going to see, so for the instance of white and black, in the case of white light, all of the light is reflected, which is why you should wear white t-shirts and light colors when you're out in the sun, because it reflects all of the light. If you have a black shirt on, or you're walking on a rooftop, or you're walking on asphalt, or you have dark hair and you're out in the sun, those things are going to heat up much faster because black colors absorb all of the red, orange, yellow, green, blue, purple, violet. They absorb all of them, and that causes it to heat up quite quickly. Okay, so then we see here, this is just an image just to show you that if you were to shine a light on a pane of glass, you're going to have a bending, an absorption, and then a transmitted. Okay. All right, so diffuse reflection. This is our most common visibility mechanism because our world around us is not smooth, and it's going to have an uneven surface. What happens is each point of light reflects in all directions, and you can see that here. All of these orange, yellow arrows are pointing out everywhere, but the ones that are in red are pointing towards the person sitting here, and those are the ones that are going to be important for forming the image in the eye. So all of these other orange, kind of tan colored ones are still reflecting the light, but they're not being detected by the eye. They might be detected by somebody else if there was a person on the other side. Okay. So this is what allows us to see areas. If you can imagine, this area around the tree is probably shaded because it's under the tree. But the reason why we can see that area in the shade is because of diffuse reflection. If we didn't have diffuse reflection, you wouldn't be able to see it under shaded areas like under a table, under a chair, under a tree. It would just be dark or light. There'd be no kind of in between of shaded. Now, the bundles of light from the object are what's detected by the eye. And remember, we talked about the colors result from that selective wavelength. So practice thinking about stuff around you. If it's red, it means it's absorbing all of the other colors except for red. Okay, so make sure you're comfortable with that concept. Now, the law of reflection is going to be the angles measured with respect to the surface normal. So normal is always perpendicular, 90 degrees from the surface. Okay, right here, so 90 degrees. Now, the incident ray is coming from the source. The reflected ray is what we detect. Okay. Now, there is a law that states if we draw a line perpendicular to the surface, the angle of the incident, which theta is always angle, and I stands for incident, is going to be equal to theta of r, which is reflected. Okay, and this is called the law of reflection. The angle of the incoming light is going to be equal to the angle of the reflected light. So image formation. Have you ever wondered why babies and puppies or really young animals are confused as to why they think that there is someone in the mirror? So this is obviously not baby 1 and baby 2. This is a reflection of baby 1. Now the baby's kissing the mirror, which is very cute, but that's because the baby doesn't understand that this is its own reflection. It thinks that it's another baby. So what's happening here is that there is what's called a real image and a virtual image. The real image can be viewed or displayed at its location. So this would be looking at your TV, looking at your phone, looking at a movie screen, a movie image on a screen, but it's the real image. Okay, it's really there, your eyes detecting it exactly where it's located. You wouldn't walk towards your TV and find out it's actually 10 feet further back than where you thought it was. Now, a virtual image, on the other hand, is where an object appears to be somewhere where it's really not. And the most common example of this is our mirrors. So if there is a mirror here, and you have a box next to you, you're going to see the box. You know the box is next to you, but it's also going to appear like there's a box on the other side of the mirror, and that's what the baby sees. The baby sees the actual image and then the virtual image. And the virtual image looks just like the real one because it's a reflection, but it's not really there. Okay. The other thing is they're going to be equally distanced apart. So the distance between the box and the mirror is going to be the same distance between the virtual box and the mirror. And then if you've ever seen funny mirrors, these are mirrors that are convex or concave, meaning they bow in or they bow out just a little bit to stretch or squish certain parts of your body. So you can see here his neck is elongated, his legs are shortened up. And so these are, but he is not on the other side, right? This guy would be standing over here, probably well proportioned. And this is his virtual image, and this is the real. All right, so what's refraction? Refraction is one that's hard to explain when we think about that box we were talking about. But refraction is where light crosses a boundary surface. So think changing from solid to liquid to gas, and therefore it changes direction. So it's really going to bend, just like we talked about with sound. So the reason is because there's a change in the light's propagation speed, which just really means how fast it's traveling. And when that happens, it produces really weird optical illusions. So one of the most common ones, if we think about the light coming in, and instead of traveling on the path it's supposed to, it bends because we're going from air to water. So something that can happen is this optical illusion right here. This pin is not bent. However, because of the water-air boundary, it looks like part of the pin is here and the other part of the pin's here. And then even wilder, we have this image. So that's refraction. It also creates a really interesting situation where if you've ever tried to catch something underwater, you may not have actually gotten its exact location because where you see the image, it might be right here. That's where you can see it. But because of the air to water boundary, the actual location of the fish is here. Okay. All right, so we're going to take a break and come back and talk about dispersion and colors on the next half of the video.